Hey everybody, Dr. White back again with section 2.4 on the binomial distribution. So, want to introduce the concept of a Bernoulli trial. A Bernoulli trial is just a special kind of random experiment where there's only two outcomes, okay? And you can call the outcomes whatever you want. I'm going to think of them as success or failure. Hit the shot, miss the shot, etc. So say that the chance of success on this trial is P, and let's denote the chance of failure 1 minus P, Q for short, okay? And let's construct a very simple random variable X. Let it be the number of successes in your Bernoulli trial, okay? So we say that X has a Bernoulli distribution with this parameter P, this probability P, okay? Very, very simple random variable indeed. Look at its probability mass function table. The chance is 1 minus P for a 0. That's when you get a failure. And the chance is P that X will be 1. That's when your trial is a success. Very simple. So other stuff about this random variable is real simple, like its moment generating function. The expected value of e to the tx would be chance of failure times e to the 0t plus chance of success times e to the 1t, which simplifies to what you see up here, 1 minus p plus p times e to the t. Okay. And using that moment generating function, you could find the mean and the variance, but I'll just go ahead and use the probability mass function, crank through with that. 0 times chance of 0 plus 1 times chance of a 1 just simplifies down to p. And the variance, well, let's see. So that's the expected value of x squared minus the expected value of x squared according to the shortcut formula. Now think about a Bernoulli. It's 0 or 1. You square 0, you get 0. You square 1, you get 1. So actually, the square of the random variable x here is just the random variable x again. And the expected value of that is a p. The square of the mean would be the square of p, so p minus p squared. Factor out a p and call it p times 1 minus p. So Bernoulli's, like, they don't really show up as their, well, they do. Look at that. They must be really important. They show up on the table of distributions as the very first entry. So we totally need to, memorize these things. The moment generating function, the mean, and the variance. And look at the clever way that they wrote down the probability mass function. Isn't that neat? They made a formula out of it, and it actually works. Like try x equals 0, and you'll actually get the 1 minus p. Try x equal 1, and you'll get the p, just like they promised. That's neat. So suppose that you perform independent Bernoulli trials. We do this a lot in practical situations. Like we stand at the free throw line and we take shots, and we can think of every shot as a trial, and it comes out as in a Bernoulli way as either success or failure, hit, don't hit. If we don't get better with practice, or worse by getting tired, if our chance of success just stays the same each time, no matter what we've done before or what we will do after, then the shots are independent. So there's a lot of situations where you're going to be performing in independent Bernoulli trials, and you might be interested in counting up the number of successes in those in trials. So let's let X be that count, number of successes in the in trials. Such an X is called a binomial random variable. Bi, two. Nomos in Greek, name, two names, success, failure. The way you write it a little bit more mathematically is X twiddles, meaning X has the distribution of a binomial random variable with N trials and chance P of success. So there's these two numbers that determine the binomial random variable, the number of trials and the chance of success. So, what are the chances for a binomial random variable to be different sort of things? Well, we're asking for the probability mass function. So let's think about this. The sample space for the random variable, the set of possible values capital X could have, there could be as little as 0 successes and as many as n successes. Okay. And what we want to do is for any x in that set of numbers, find the probability that capital X turns out to be that particular little x. So it seems like this might be a bit of a complicated problem. So to gather some insight on it, let's work with a specific example and then see if we can generalize our thinking. So why don't we let x be the number of heads in 5 tosses of a weighted coin, where every time you toss the coin, the chance is p that it comes up heads. Okay? Then x is binomial, where the number of trials is 5 and the chance of success is whatever it is. Could we find the probability of getting 3 heads in your 5 trips? So if we think about it logically, the probability that x is 3 can be thought of as the probability of this event, x being 3. It's actually the union of 10 disjoint events. There are 10 ways to have 3 heads in 5 tosses of a coin. I know this because if you're going to have 3 heads, you got to have 2 tails. And so you're working with HHH and TT. And all the ways that it could come out where there's 3 heads is just the number of ways you could spell a word, with 3 H's and 2 T's. And I'll explain to you in a little bit, but I happen to be able to figure out right away that's going to be 10. So there's 10 events that are getting unioned up there, and I just didn't have, I didn't care to write them all down, but just wrote down 3 of them, and then ... But it's a disjoint union of these events. And let me get the probability of a few of those events in that disjoint union. Like, what's the probability that you get your 3 heads, then 2 tails? Well, that would be p times p times p times chance of failure, q, 1 minus p, times q again for the second failure. So p cubed times q squared. On the other hand, it could have come out where you get heads, heads, tails, then heads, then tails. And that would be p, p, q, p, q. But that's still 3 p's and 2 q's multiplied together. No matter how you work it, if you start with a sequence of 5 that's 3 heads and 2 tails, then commutativity of multiplication is going to have you with p cubed times q squared at the end. So all we really got to think about is, like, how many ways are there to get 3 heads and 2 tails? And then we can multiply p cubed times c squared by that number of ways. That'll be the probability of this union here. Well, it's pretty easy, because remember when we learned how many ways to spell the word Mississippi? You take the number of letters, factorial, and then you divide by the numbers of same letters, factorial, all the way through. So 5 factorial over the 3 heads, factorial, divide again by the 2 tails, factorial. And that's the same as 5 choose 3, which totally makes sense to me, because it ought to be the number of ways to pick 3 spots out of the 5 to hold your heads, the remaining being forced to hold tails. It really is just a choosing problem. And so the probability that x is 3 would be 5 choose 3 times p cubed times the q squared, 1 minus q squared. So you can generalize your thinking here. If you've got any old binomial random variable with n trials, and you want to know what's the chance of x successes, it would be n choose x. P to the number of successes, 1 minus p to the number of failures, which is n minus the number of successes. So great, we've got the probability mass function. So we could find probabilities now for binomial random variables, using that. But because it involves the combination formula, it can be a little bit tricky to work with the calculator and things like that. So we'll use R to compute our binomial probabilities, if you don't mind. So tell you what, I'm going to just break this screencast right now, but I'll come back and we'll come back and get into R and work with binomials there for just a wee bit. Okay. That means I got to stop. See you later.